So in this segment, we're going to be taking a look at another special case. And this special case is one that we're familiar with. We've run across this concept of an autonomous differential equation before. And that's when the right-hand side of the differential equation, everything that's not the derivative, depends only on the dependent variable, right? So if it's a function of, or your derivative is dy dt, then the right-hand side would only involve terms having to do with y. They wouldn't have anything to do with t, right? So these are referred to as autonomous differential equations, and they're really, really useful. They get used all over the place. So let's take a look at an example. And in this example, we're going to presume that we're throwing a baseball straight downward from a helicopter at a specific altitude of 3,000 feet. Turns out that the dE, the differential equation that models this situation, is dV dt equals 32 minus 0.16 v. Now you might be wondering where do these numbers come from, but first let's break down the equation. And what is it saying? This is literally saying the rate of change of velocity. So this is the rate of change of velocity of the baseball. And it turns out the rate of change of velocity only depends on velocity. It doesn't depend on time. It only depends on velocity. Right? So how quickly the velocity of the baseball is changing depends on how quickly the velocity, or how quickly the baseball is moving at any given moment. And so let's take a look at what this looks like if you were to do a dE plot. What would this look like with a bunch of solution curves? Well, it looks like this, where we've got, notice our axes here, we've got in this direction t, and in this direction v of t. So we've got velocity in this direction and time in this direction. So what you're seeing are a whole bunch of initial conditions here, 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 here. All of these are separate curves. And they're all different initial conditions. And so, for example, up here, this initial condition is saying at t equals 0, the velocity equals 400. So that's you throwing the baseball straight downward at 400, I don't know, feet per second. We're not really given units other than altitude of 3,000 feet. So I guess feet per second maybe? Now, if you're throwing a baseball at 400 feet per second, you've got a monster throwing arm, so that's pretty amazing. But suffice it to say, what happens to the velocity of the baseball if you throw it straight downward from this helicopter floating in the air at 400 feet per second downward? Immediately, as time goes by, the velocity of the baseball starts to decrease. Why is that? Why would the velocity of the baseball decrease? If it's going downward, you'd expect it to speed up, right? Well, that's the velocity is going to speed up part of the term. This right here is the part of the rate of change of velocity that's due to gravity. And those of you who have had a little physics before probably recognize that number 32. This is the gravity part of the rate of change of the baseball. So gravity's pulling downward at a rate of 32 feet per second per second. So it's going to speed up your baseball in the downward direction. But wait, there's another term. This term right here is something different. This term right here is saying as the velocity gets bigger and bigger and bigger, this term's going to get larger and larger, negative. And at a certain point, this term will be so big, it'll overwhelm gravity. It'll be even bigger than the contribution due to gravity. So what you're actually seeing is a second term right here that's pulling in the opposite direction of gravity, and that's called drag, or viscosity if you want to get fancy about it. But most of us think about air resistance when we toss objects around, right? If you crumple up a piece of paper and throw it, you have to think about air resistance, and that's exactly what this term does. And that's why if you start with a velocity of 400 feet per second straight downward, your velocity actually decreases over time. But let's look at the other end of things. What about this guy right here? What's going on with that initial condition? Well, at t equals 0, this thing has a velocity of 0. So that's basically you going to the door of the helicopter and going boop and releasing the ball, and the baseball is just going to fall. In other words, its velocity is going to get faster and faster and faster. It's going to speed up. But notice, it doesn't speed up forever. It gets faster, but then it sort of tapers off. The tapering in this direction, the tapering in this direction, that's because of this drag term. As the velocity gets higher, it gets closer and closer to what we might call a terminal velocity. So down on the bottom here, you'll notice a couple of things. That the first question says, based on this slope field diagram, what can we say about the ball's velocity exactly 10 seconds after it's thrown? Well, 10 seconds after it's thrown would be right here. And that means anywhere along this kind of vertical line would be 10 seconds after it's thrown. The problem is, what can we say about the ball 10 seconds after it's thrown? Well, we can't say much because it could be any one of those curves. It could be any one of an infinite number of curves. So the trouble is, we can't tell whether it's speeding up or slowing down. We can't tell whether it's a really big velocity or a really small velocity. The only thing that we can say for sure is it's somewhere along that vertical line. So the short answer is, without an initial condition, we can't say much. In fact, we can't really say or predict anything specific. So this graph is great for some things, but not for others. What's it great for? Well, that's the second question. What's the speed of the ball in the long run? Now notice, I'm saying what's the speed of the ball in the long run, and I didn't say anything about an initial condition, because regardless of the initial condition, what happens to the speed in the long run? Well, everything heads towards this particular straight line, horizontal line right here. If you start up here, it tapers off towards that solution. If you start down here, it tapers up towards that solution. And it looks like it's in the ballpark of about 200. So it looks like all roads lead to this horizontal, you could call it an asymptote if you want. We're going to have another name for it. Because if you were to plug in larger and larger velocity values, higher and higher velocity values, over time, it doesn't matter. They're all just going to taper off this way. So regardless of the initial condition, we see there is an equilibrium. Oh, sorry, let me scoot down. An equilibrium solution of about 200. And again, this is a limit argument. We're saying in the long run, and what we really mean is what's the limit as t approaches infinity. This phrase right here, in the long run, is code for as t approaches infinity, right? And we can see what's happening. As t approaches infinity, we expect the velocity to approach about 200. And just so you can see the code for this, where I created that graph from, let me show you. The code for this graph right here, with its solution curves, I just kind of changed the scale, and you can create that exact same thing. No, that's not the same. Oh, that's not even the same one. I thought it was the same one, but it's not. So disregard this. The punchline is, if you have a differential equation that's in terms of only the dependent variable, you have the same slope, not vertically, but horizontally. So you can see no matter where you look horizontally on this graph, the arrows are always pointed in the same direction. If you go down here, horizontally, the arrows are pointed in the same direction. And that's because, in this case, we've got a differential equation that's only in terms of the dependent variable, an autonomous differential equation. Okay, so that's where we'll start, or we'll stop here. There's one more page where we're going to kind of bring it all together, and we'll do that in a separate video.